Edwin Hubble was the first one to discover the expansion of the universe with the red shifts that he noticed. And that was the first piece of evidence that the universe was expanding. But it wasn't immediately accepted. There was definitely controversy. There was, the going theory at the time was that the universe was stationary, was static. But since that time, we have discovered other pieces of evidence that support the idea of the Big Bang, okay? And one of the first things was in 1948. This Russian physicist, George Gamow, and Ralph, actually his last name's Alpher, I believe. I've missed the L in there. They thought about this idea of the Big Bang, and they said, hey, if the universe was once small, it would have been incredibly hot and incredibly dense. And if it has been expanding since the beginning of time, then just like any substance, as it expands, it becomes more dilute and it cools. And they did some calculations and some thinking, and they said, hey, if that's true, the universe should be an average temperature of 5 to 10 Kelvin right now. And that was kind of cool. That was in the 40s, and it was just an idea. They calculated it, they thought about it. They didn't have any way to test it, but they said that's kind of what the temperature of the universe should be. We'll come back to that in just a second. A little bit later, okay, and I don't know the year, it was discovered that there's helium everywhere. Hydrogen is really, really the dominant thing. Hydrogen is the #1 element out there. But helium makes up approximately 25% of all stars. You do not find stars with less than 25% helium. This was attributed to the idea of the Big Bang, because we know that stars make helium, right? We know that stars fuse hydrogen into helium. But why do they all have 25%? Well, what some people theorized was that in the early universe, if the Big Bang is true and the expansion of the universe is true, in the early universe, the temperatures would have been high enough so that fusion would happen. And the helium of the early universe would have actually fused into hydrogen. Into helium. The hydrogen would have fused into helium. When they did calculations, they said, hey, if this is true, there should be about a 75-25% ratio. And lo and behold, that's actually what we measure. All stars have at least 25% helium, and that's more than could have ever been created in the star itself. So that was another piece of evidence that the Big Bang is potentially true, that there was a very hot, very dense early universe. So that answers. So then we move forward in time, and in the 1960s, this basically was the idea of where that helium came from, that in the early universe, it would have been hot enough and dense enough to actually fuse these first atoms of hydrogen and fuse them into helium, and that's what accounts for that excess. Now, the final discovery, they call this like the smoking gun. In this video you're going to see, they talk about finding the smoking gun that definitively would prove that the Big Bang happened. Well, the crazy thing is, these guys in the 40s predicted that the universe should have a temperature of around 5 to 10 Kelvin. In the 1960s, there were two scientists working for Bell Labs on the East Coast and named Penzias and Wilson. And they had built this huge microwave receiver in order actually to communicate with satellites and do some other things. It had nothing to do with astronomy. They were actually trying to do satellite communication with this big receiver. And they couldn't get it to work right. It always had this static in it. And they thought it was broken. They actually went and, at first they thought maybe it was broken, and they tried to calibrate it. They aimed it different directions. It always had static in it. They actually, at some point, thought that bird poop had, totally messed it up, and they went and they kicked the pigeons out that were living inside of it, and they cleaned it out, and they got it out. They could not get rid of the static. What they finally recognized is that they were receiving energy. They were receiving radiation from all directions. It wasn't a point source. It wasn't coming from the sun or a galaxy. It was coming from all directions. It appeared to be coming from everywhere in the universe. And remember, we talked about black body curves. Well, when they looked at this radiation, remember, the cooler an object is, the longer the wavelength it radiates. And what they found is this energy that they were receiving was radiation that was being given off by an object that has a temperature of approximately 2.7 Kelvin. They essentially, by accident, measured the temperature of the universe. They were detecting radiation that these guys predicted in the 40s should be about 5 to 10 Kelvin. They found it at 3 Kelvin, and that was the Big Bang. That was energy that was released 300,000 years after the Big Bang, as soon as the universe cooled enough so that energy could actually be released. And at the early times of the universe, it was incredibly hot energy, very high, short wavelength, high energy. But as the universe has expanded over the past 14 billion years, it has cooled to 2.7 Kelvin. This was the definitive piece of evidence that the Big Bang actually happened. I mean, redshift was great, excess of helium, great, but the cosmic microwave background was another huge piece. And since this was discovery, these guys, by the way, won the Nobel Prize for this discovery, even though it's kind of wild that it was totally an accident, if you think about it, but they still got the Nobel Prize. This was not WMAP yet. This was the discovery of the microwave background. Very rough at this point. It was just like, wow, there's microwave energy coming from all directions. Then we built more sophisticated satellites to map it even better. And WMAP is one of those telescopes that did that. Let's look at it a little bit. Here's Penzias and Wilson. There's their telescope. Okay, notice it wasn't a telescope when they built it. Again, it was meant to communicate with satellites in the microwave frequency, and it was this weird, mysterious static that they discovered was, again, it was an accident. They discovered this what we call the cosmic microwave background, the microwave radiation from the universe that really is the earliest universe we can see. That is the energy that was first released after the Big Bang. Once the universe cooled enough so that photons could freely travel through the universe. What's that? So here's a map of the universe in the microwave region. Okay, and actually it kind of comes from this. I kind of like this. When we look at these three pictures, here's what you get. When you take a microwave map of the universe, the first thing you get is this kind of yin-yang symbol up here, and that's because we're moving. And in one direction we look, all the radiation is going to be redshifted, and in the other direction we look, it's all going to be blue shifted. Okay, and that's this picture. Okay, so that was the first image they took. It's like, wow, check that out. And if you think about it, that is actually, when we'll talk about reference frames in relativity, that there is no absolute reference frame. But in some ways, the cosmic microwave background could be thought of as an absolute reference frame. It's everywhere, and this is our motion against that background. When they subtract that motion out, the redshift and blue shift, and they take it out, this is what you get. And then you still have this swath in the middle, which is the Milky Way, which has got some radiation involved with it because of heat and things like that. So then you subtract that, and this is what's left. And this is the map of the universe. And a couple things to notice is that it's not uniform. So even as early as 300,000 years after the Big Bang, the universe was already starting to not be uniform anymore. It has areas of higher density and lower density, and they believe that this is the beginning of the formation of stars and galaxies and things like that, because you have regions of higher and lower density. The other thing that I don't understand fully, but that I've read about some and that they talk about, is that it's incredibly close. It's actually almost uniformly dense. It's very, very close. Right, really, really, really close. And that is what leads to this idea of inflation, the inflationary theory, that there had to be a period of rapid, rapid growth so that everything is uniform enough to be the way we see it today. Okay? So here's our basic model then of kind of where we are, what's going on. There was a Big Bang, there was a beginning of time, and everything was compact and dense, and there's been expansion ever since. As the universe has expanded, it has cooled, structures have formed. This whole process has taken on the order of, 13.7, somewhere around 14 billion years, we think. But that number is always being refined. And again, knowing Hubble's constant helps us figure out the age of the universe. Okay, so that's kind of that cool connection. So let's look at the possibilities then. We know the universe is expanding. Let's look at some possibilities and some models. And again, we think of it as an explosion, but I don't think that's a good model. The raisin bread, I think, is a better model, because an explosion, you think that everything's moving away because it has its innate velocities. But really what's going on in the universe is that galaxies aren't necessarily moving really rapidly, even though they do have motion, but it's the space between them that's growing. And that's why the raisin bread works well. If you imagine like a big, immense loaf of bread with raisins in it, and each raisin's a galaxy, as that bread expands, right, when bread rises, it expands, all those raisins get farther apart. Not because the raisins are flying through space, but because the space between them is expanding. That's really what's kind of going on here. Okay? Okay. All right?
I have a question about that, about the expansion of space.
Okay. Let me think about this. Let me just do one thing, and then remember your question, Vince. Okay. So we talked about the light we see being redshifted, and before we talked about the Doppler effect happening because an object is, imagine like a siren. When it's moving towards us, the sound changes. When it's moving away, the sound changes. The cosmic redshift is different. We see redshift not necessarily because the galaxy is moving away so fast, but because that photon as it travels through space, the space gets bigger, stretching the photon out and making it longer, redshifted that way. Okay, that's another way of thinking of the redshift of the universe. Okay, look, there's the raisin bread theory. Got it? Good. Okay. Here's the cosmological redshift. Okay, again, it's not that the star itself is necessarily moving away, though that can cause a redshift, and we see that a lot. But if something's really distant and it's emitting photons, as that photon is traveling, the space is expanding and therefore stretching it out and giving it a redshift. So it's just a slightly different way of thinking about it. So let's go back to where we started with Olber's paradox. Okay? So remember Olber's paradox that why is there darkness, right? According to Newton's view of the universe, if you think about Newton's view that the universe is infinite and static and uniform in all directions, then there shouldn't be any darkness because any direction you look, you're eventually going to get to a star or a galaxy, so you should see light from it. So you should see light in all directions. That was Olber's paradox. So let's look at some solutions to Olber's paradox now that we know what we know. First of all, there's a finite amount of time, 14 billion years, that the universe has existed. So it's impossible for us to see any object that is further away than 14 billion light years away because the light has not had time to get to us. So that's one solution. So there can be darkness because there's a finite distance that we can actually see things. Okay? That's one possibility. Another possibility is that the expansion of the universe can shift the light of distant objects, either dimmer because of the expansion, because of the redshift, but it can even redshift out of the visible wavelengths if it's far enough away. That's another possible solution to Olber's paradox. And this third one is kind of what I talked about at first. Okay, there hasn't been enough time for the distant objects, the light from distant objects, to actually reach us. So these are solutions. These are some possibilities as to why we do have darkness, why the night is not infinitely bright. So we have this idea of a universe. Now here's the thing. If the universe is not infinite in space, if it is finite in space, there's a variety of ways of trying to comprehend it. But first of all, the question that always comes up is, well, if it isn't infinite, what's beyond it? What's outside of it? And there's always that discussion like, oh, well, maybe we're just a little atom inside of the stomach of a big giant, and all that stuff you think about. But beyond that, the question is actually kind of absurd, okay? Because by definition, the universe is everything, okay? So if someone comes up and says, like, hey, what's left of Wednesday? That's kind of an absurd question because, like, no, it's not. It's like, time is different than left and right and up and down. You know what I mean? And so it doesn't make sense to say what's outside of the universe because the universe is everything. And the Big Bang was the beginning of both space and time. That was when our universe began and when time began in our universe. Now, it is interesting, and we do discuss multiverse theory and multiple universes and things like that, contemplating what else could be out there. But for us, really, this is it. Now, in terms of the size of the universe, it makes sense to me that what we can see is this little bubble of 14 billion light years, because that's how old the universe is. That's as far as we can observe. But the universe itself, they believe, is actually much, much larger than that. And the analogy I heard recently was that if you imagine what we observe as being like the size of a stamp, a postage stamp, then they think the actual universe, if that's our observable universe, they think that the actual universe would be like the whole Earth or something like that, relatively, okay? How they know that, I have no idea, okay? Because how can you know that? Okay. So again, here we are, all right? This is kind of an idea of, here's the Milky Way galaxy, and we're looking out from it. And once we look out about 14 billion light years out, we start to see the beginning. That's the cosmic microwave background, right? But it actually isn't there anymore. The universe is much, much larger than that, and we can't observe it because there hasn't been enough time for the light to get to us from these other places, okay?
So technically we are in the center of the universe?
Everyone is. There is no center, or everyone is the center. It depends on how you want to look at it. This is a bad drawing. Don't think of it as a big sphere. So this is always a fun question too. Like, so we know pretty well what's happened in the past. We're developing better theories for the evolution of the universe. So now let's stretch it out to the forwardness. Let's look ahead. What's going to happen? And if you think about what's happening, the universe is expanding, and you think about gravity, and that gravity is an attractive force,
But it's very
yes, there seems to be three possibilities that have always been thought about until about 10 years ago, and which I'll tell you in a second. But let's think about this first scenario. And the idea is this. You can have either an open universe, a closed universe, or a flat universe. An open universe is a universe that is expanding like it is now, and there's not enough matter out there to slow the expansion. It'll slow down, but it'll expand forever. That's the definition of an open universe. A flat universe would be one where the mass of the universe is just right, so that the gravitational attraction will slow the expansion to a point where it just stops at some point, and it's zero, and it just stays there. That's flat universe. And the crazy thing about this, I was reading this the other night, I was like, wow, I never thought about it that way. If we have just the right amount of mass for a flat universe, if we have one electron more, just one more electron, the universe will start to collapse in on itself, right? There's like this perfect balance. That would be flat. Now, a closed universe, there's enough mass that the expansion slows down and actually stops and starts to contract and collapses in on itself into what's called a big crunch. And you have a big crunch, and then, in my mind, you'd have another big bang. And the whole universe just kind of bounces through ever, right? Forever. Michael. So in this model of the fate of the universe, where we're looking for whether or not the universe is open, closed, or flat, the thing to know, the thing to try to figure out is what's called the critical density, or actually just the density. The critical density is a number. The critical density is the density of the universe that would create a flat universe. Okay, the critical density, if the density of the universe is the critical density, the universe's expansion will eventually stop. Does that make sense? If the density of the universe is actually greater than the critical density, we say that we have a closed universe. And if the actual density is less than the critical density, we have an open universe, and it'll expand forever. Okay? These are incredibly challenging things to measure, the density of the universe. The critical density is the density of matter in the universe that would cause the expansion to stop. It would create a flat universe. Okay? Above that, this is what some people do. They sit around and calculate and think about and measure these things. Okay? Now, there's another way of trying to measure what type of universe we live in, open, flat, or closed. And another way of measuring it, other than looking at the density, is to look at the geometry of the universe. Now, again, imagine we're on a postage stamp. The universe that we can observe is a postage stamp, and the rest of the universe is the entire Earth, okay? And trying to measure that geometry. And here's how it works. You guys have studied geometry in school probably a lot, and you usually study geometry, what we call Euclidean geometry. It all works great on a flat surface, right? A triangle, the angles of a triangle add up to what? 180 degrees. And that is true if space is flat. But if space is not flat, that's not true, okay? For example, if space is curved spherically, okay, this would be where the density of the universe is greater than the critical density. This would be a closed universe. And notice I've drawn a triangle here. It's still a triangle, but now if I measured these angles, they wouldn't add up to 180. They'd be greater than 180. And I would know that we live in a closed universe. How awesome is that? If the universe is flat, if we have the critical density of the universe is equal to the actual density, and we have a flat universe that's going to eventually stop expanding, then the angles of a triangle would add up to 180 degrees. That'd be beautiful. If it's an open universe that's going to expand and expand forever, they talk about it being a hyperbolic space. I can't visualize the geometry of it. They talk about saddles. But notice, drawing a triangle on this shape, the angles add up to less than 180 degrees.
Well, that's kind of the...
That's the question. Now, if you just drew the triangle on a piece of paper and tried to measure the angles, the size of the universe is so big that you would never be able to determine whether it's open, flat, or closed. But if you were to launch 3 satellites out into space that had lasers and had super precise measurements that could measure those angles, you could actually measure the geometry of the universe and figure out which one it is. We don't have the technology to do it currently, okay? It's a great, whoops. Now, let's go back to a closed universe for a second. Now, if space is curved this way, imagine the universe is actually like a giant sphere. We talked about this a little bit the other day. This makes a little bit more sense to me in terms of infinity and non-infinity. If the universe is closed like this, it's spherical, It is infinite. You look in any direction, you will never see the edge. You will always be moving on it. So we call it infinite and unbounded, right? That makes some sense to me. This one, the same thing. It's kind of infinite in all directions. You never get to an edge. Hyperbolic space doesn't make much sense to me. But the big picture of the fate of the universe is this. Here's what we're really looking at, okay? Here we are today. Here's the Big Bang. The universe we know has been expanding. This is what we're observing right now. If the density of the universe equals the critical density, then this expansion will slow down and eventually stop. If it's less and we live in an open universe, the expansion continues forever. And if the density is greater, then we end in a closed universe and everything crunches together, and then maybe another Big Bang happens. Now, for some reason, now, a couple different things to talk about here. One, my personal preference. This is important. I believe in cycles. Nature seems to work in cycles. It makes great sense to me that the universe would be cyclical, that we would expand, grow, collapse, die, and redo it, because that's what I observe in the world around us. So that's my personal preference. When people measure the density of the universe, it appears to be incredibly close to being flat. That's the observation right now, is it looks really close to being a flat universe. The ridiculous thing that messes all of this up, unfortunately, is what was discovered literally within the last 10 years. And two different groups that were measuring type 1a supernovas and trying to measure the rate of deceleration of the universe, how fast it was slowing down to try to figure this stuff out. Two independent groups at the same time discovered that actually the universe is accelerating in its expansion, okay? This is where dark energy comes from. What is causing the universe to speed up? Because our understanding of gravity says it shouldn't be. It should be slowing down, and it's not. So either we don't understand gravity, or there's some energy, some other dark energy, some force that's pushing, overcoming gravity now, okay? And that's what they call dark energy. They know its percentage value. It's like makes up 75% of the universe or something like that, right? But no one knows what it is at this point. So either we don't understand gravity well enough, or there's some other thing going on that's causing this acceleration. And that literally is last 10 years this was discovered, okay?